Good afternoon, everybody. This is Roger Frechette. I'm the managing principal of Interface Engineering, and I want to welcome everybody today to the next installment of our Interface Engineering educational webinar series. I see a lot of people are signing in right now, so I'm going to give everybody about a minute or so to allow a few more people to join in, and then we'll get started. Thank you. Okay, well, it looks like the number of attendees have doubled in the last minute, so I think we will get started now. Again, my name is Roger Frechette, the managing principal of Interface Engineering, and we are for those of you who do not know us, we're a 51-year-old mechanical, electrical, plumbing, engineering design firm, and today we are going to be presenting the next installment of our educational webinar series, which will run through the remainder of the summertime and into the fall. And today I have the distinct pleasure to introduce our speaker, Mr. Kevin Cahill. Kevin is a principal with Interface Engineering in our Washington, D.C. office. He is a licensed professional engineer and a LEED accredited professional. Kevin is a graduate of Worcester Polytechnic Institute, WPI, in Massachusetts. Kevin has led the engineering and been responsible for a large number of high-performing buildings across the United States and around the world as well. He is a former recipient of the 40 Under 40 award from Consulting Specifying Engineers. Kevin is my partner, and he is an all-around good guy. So without further ado, Kevin, why don't you take it away?
All right. Thank you, Roger, for the nice introduction. I guess that 40 Under 40 award was probably a few years ago, but in any case, thanks, everybody. I'm going to get started here. We're talking about high-performance buildings, net zero schools that make the grade. We're using Meridian High School in the city of Falls Church as our case study for this example. For those that don't know, Meridian High School was just renamed. It was formerly known as George Mason High School. Meridian High School was renamed, I believe, on April 28th of this year. And one of the reasons for calling it Meridian is the school's long history of education for global citizens through international baccalaureate program. But the other reason was that city of Falls Church was the original meridian between Virginia and Washington, D.C. It used to be the line delineating those two. So kind of an interesting geographical fact there. So I would be remiss if I didn't mention the team for this project. So certainly Falls Church City and the city of Falls Church has been instrumental in this project. Brailsford and Dunleavy representing the owner as the owner's representative. It was a design build. It was a contractor-led design build delivery method, so that our teaming partner was Gilbane Construction. Two architectural firms teamed to do the architect interiors in the site. That was Stantec and Quinn Evans. Thank you to Stantec for the image, I think, in the background that I took. Interface Engineering, of course, and then our trade partners, and by trade partners I mean the subcontractors, construction subcontractors, which was Pro Air Mechanical, Free State Electrical, and others that made this project possible. So our learning objectives today is we're going to talk a little bit and define the definition of net zero and net zero ready, why K-12 schools for our high performance are great for the design process, a design process and decision making in a design build approach to net zero schools, and the implementation and combination of strategies to achieve net zero. So jumping right into it, the definition of net zero, this is the definition put out by the Department of Energy, a common definition for zero energy buildings. This was put out in September of 2015. It's about a 40-page document if you care to read it, which is interesting to get just a simple definition. However, the definition provided by the U.S. Department of Energy is determined as an energy efficient building where on a site energy basis, the actual annual delivered energy is less than or equal to the on-site renewable exported energy. So really what that means for our project is on an annual basis, it becomes very important that we talk about it on an annual basis. So on an annual basis, a net zero project will generate more power than it will consume. Some of the measurable high performance criteria, this is high performance buildings for schools. This is generally the measurement of the high performance criteria, as well as I believe this was the criteria identified in the RFP in terms of the maximum energy use intensity, the overall R values, thermally broken windows, air tightness, and making the system straightforward to operate and control, make them easily maintained. And I'll go through all of those criteria as we go forward. The definition for net zero energy ready is not as well known and not as formally documented within the industry. So, but we were able to find some national references that it is an energy efficient building with the goal of being net zero energy at some point in the future. So the example we give is for this project where the addition of the photovoltaic panels for the on-site power generation was in the future, or in this case, it was actually done through a power purchase agreement. So the building itself and all of the envelope mechanical electrical systems were all set up to be net zero. And then the missing piece is the power generation, which is underway, which is under design and should be starting construction here shortly. So, but for our purposes, it became net zero ready for discussion. So why pursue net zero energy for schools? Why does it make sense to do such a thing? And really, it's the energy demand. We talked a lot about George Mason High School. Sometimes I joked that it was really a community center that taught high school during the day. So there's over 100 different groups that use this facility within the city of Falls Church that are not necessarily high school related. So, example is they would rent the current high school out to a church on Sundays to use as their facility. So, and they use it for voting and they use it for a whole bunch of things that are not necessarily high school. So the energy demand for such a building is high. And generally speaking, the plug loads are pretty low. And we'll talk about how we control some of those moving forward. The high renewable energy potential of a high school or any K-12 school really is pretty high, given that for most part, you end up with 1- and 2-story schools with a roof that can be liberated of mechanical equipment. So the roof areas can become almost exclusively used for power generation. It's owner occupied. We hope this building will be there 50 years plus. Certainly the existing high school has been there for more than 50 years. So as an owner occupied building, they certainly are interested in reducing their operating costs, and anything that pays itself back, obviously they're paying themselves with those paybacks. So that is another reason owner occupied buildings become very attractive for net zero energy. We create a better learning environment. A healthier, more comfortable indoor environment stimulates the learning for the students. We know that to be true in terms of daylighting and healthier building, better ventilation. All of those things contributing both to the educational component as well as reduction of energy and energy performance. And last, schools already have a sustainable mission, so to provide living labs and a growing curriculum to emphasize technology and the environment. So the definition of energy modeling, I'm going to take a half a step back here and talk about energy modeling for just one moment. So in energy modeling, at least on our coast, others use Title 24 in California, for example, but the methodology used here on the East Coast is Appendix G almost always as a rating method. And Appendix G in ASHRAE 90.1 has two systems we always talk about, the proposed design and the baseline design. Both are a computer representative of the building. And in the baseline case, we're talking about a project with minimum prescriptive code requirements. That would be the prescriptive requirements of the code that are the minimum of what you would be allowed to build. And then our proposed design, which is the actual building design of what was constructed. When we look at the Appendix G, and for energy modeling software, there's a whole host of softwares you can use. In our case, we actually used Energy Plus and Design Builder for this project, but certainly there are others that are applicable, with almost all of them running on the Department of Energy platform or the DOE2 engine. So the components of an energy model, when you go to Appendix G, there's 13 sub-chapters or chapters within Appendix G. And you'll see the comparison of the proposed design in the middle there and the baseline design on the right. And so many of those things, when you compare the components of an energy model, need to be identical. In other words, the building model itself needs to be the same. You can't compare a square building to a round building. Schedules are the same. The occupancy is the same. So when we really get into what can you control and compare to a minimally code compliant building to a proposed design building, we're really only talking about 4 components. So the components of building envelope, lighting, HVAC, and service hot water. And service hot water is really your domestic hot water system for sinks and showers. There is one additional component that you can change for your proposed use, receptacles and other loads. It requires an alternate calculation, which we did for this project as well. But so it's really those 4 components. Everything else, if you look at, is in the comparison of baseline to design is the same. So we really focus on the first 4 and then the supplemental 5th category when we really look at net zero energy buildings. So the project overview for those that don't know, it is on the western end of the city of Falls Church. It is at the intersection of Route 7 and 66. It's right in the corner, right next to the Virginia Tech campus. It is next to the existing Mary Ellen Henderson Middle School, which you can see as you drive through on Route 7 as you're heading into Tyson's Corner on your right. And the project was able to be constructed on the existing high school campus, and then the existing high school itself is actually going to be demolished and turned over for commercial development. That's part of that the financial deal for the project. This is a pretty good image where you see where it says Mary Ellen Henderson Middle School in the middle. The middle school is to the left side of that, and the high school is sort of to the right of that, or to the northeast of that. I like this view. To give you a better understanding, there's the opposite view that I just showed you, where all of the roofs that you see in gray on the right side is the existing middle school. All of the roofs in white and green on the left side, that is the addition of the high school with the 2 wings that you can see, and then the connector is really a common shared cafeteria, and dining is shared between the high school and the elementary and the middle school. So this gives you a section of the building. This is just a cut through the building where it's a 7-story building with the lowest level being largely locker rooms. Below what is the 2nd, 3rd levels, the G1 or B1 level, and 1st and 2nd levels being high bay spaces. So there's a competition gym, an auxiliary gym, and the auditorium are in those high bay spaces. And then you'll see on the left-hand side, levels 3, 4, and 5 that stack up above those high bay spaces. And then on the right side, what we consider the skinny bar on the right, you'll see where 2, 3, and 4 are those program elements. The center connector of those 2 bars is the heart of the school with an interconnecting open stair all the way through. Just kind of gives you a sectional view of the overall. So for our high performance design process, we look at 4 steps to achieving a high performance building and net zero energy. We look at reduction strategies, reclamation strategies, absorption strategies, and generation strategies. And we break them down into those 4 elements. The reduction strategies is reducing either the demand on the building or our consumption on the building. Examples of that might be an improved building envelope to harden ourselves against direct solar radiation, for example. Our reclaim strategies, reclamation strategies include taking energy that would otherwise leave our building and reusing it prior to allowing it to exit the building. Our absorption strategies, we're absorbing natural resources. In our case, our absorption strategy is really a geothermal system, which I'll go to in a minute here. And then last is generation strategies, which almost always are integrated photovoltaics on the roof of the building to generate power. So this is our how-to. Again, we're focusing on space heating, cooling, mechanical systems, lighting, and service hot water, as well as the building envelope when we look at all of those different strategies to incorporate into the process. We looked at a baseline energy performance diagram. We ran the building through its paces, and a minimally code compliant building, this was the initial look at what a baseline building would be and where all of those energy sources go. So you'll really see here that a lot of our energy goes to heating, cooling, lighting, and plug loads. And again, that's why those 4 elements of the project become a pretty major focus of where to put the energy and efforts into getting reductions and reducing our energy consumption for net zero. So the sustainable strategies, the reduction for the building envelope. Here we're looking at 2 building models where we took insulation values on the left side for the wall insulation, and we ran it with different values from R10 all the way through R30, with R15 being the baseline. And we selected an R25 insulation value for the walls. And we do the same on the right-hand side where we look at insulation values from R15 to R35. And those, and we see the improvements of what happens over time. It is the case with insulation that more is better. However, you start to see diminishing returns right about where we selected, about the R25 on the wall and the R30 for the roof. You start to see that the delta or the increased gain when you jump up to that next level, it starts to diminish. So their return on providing that additional 5 of insulation isn't quite there. So that's why we sort of stop at the R25 and the R30. Same with the glass. So on the glass for this project, we went through about 13 different glass types that we looked at for the whole project. We looked at different solar heat gain coefficients, U values, and visible light transmittance all the way through. These are glass types that you can buy. By and large, we're looking at solar band and Vericon glass types all the way through. And then working with Gilbane, we were able to put prices to this. So it's not always about picking the lowest energy performer here, which would have been number 10. But it's about understanding which glass type gives us the best performance per value and how we select that glass. So I think actually in this project, we're actually glass number 7, which did not provide the best performance. However, it was the best performance for the dollar and what we spent to get that performance and what the cost of that glass was. So that was 1. Okay. So one of the issues with our project is that we did the solution was to build a vertical high school, again, the 7 stories. And what that allowed for was to give us additional land area to get the fields in that program in, the multipurpose field, softball field, tennis courts, etc. the baseball and football field remained untouched there as they were before we started. So the building, actually, its orientation is not perfect. So one of the things we were challenged with, and rightfully so, during the design was some of the glare analysis that could happen as we had the building not oriented perfectly kind of east-west. So our north-facing glass windows and our south-facing windows are actually facing northeast and southwest. So we did an analysis where we looked at the radiation dome for the classrooms at the orientation we had. And within that, we looked at the minimally code compliant glass and what that would mean in terms of sun hours and then the radiation into the building. So you'll see here the hours of glare and glare control and the percentage of the space that had more than 250 hours that were going to be considered to have glare. When we took the glare by season, and then we were able to isolate it, essentially what was in the upper left, you see the spring semester, and the upper right, you see the fall semester. And then when we further looked at that analysis and we isolated it really to the classroom hours between 5 and 8, and then 8 to 3 in the bottom left and bottom right. In the bottom left, we actually, as you can imagine, got a lot of glare between 5 and 8, and that had to do with the morning sunrise. However, in that analysis, looking to the northeast from 8 a.m. to 3 p.m. during classroom hours, that glare was substantially minimized, and it was less than 3%. And we felt that that was, that 3% was well within our tolerance and well within our control, and something that we could live with within the space, the proportion of the space that was going to have a glare problem. It's about 3% of the floor area really on the perimeter during those school hours. So it became really a non-factor for us, but it was worth studying just to make sure that the orientation didn't have substantial adverse effects on our energy use. Then we got into our lighting strategies, reduction strategies for lighting. We're trying to reduce how much lighting is on and then what the lighting power density is. So we were able to work very closely with the electrical contractor as well as the electrical supplier, the lighting supplier, and we came up with this diagram. And this diagram identified all of the RFP requirements along with all of the code requirements and all of the lead requirements all on one sheet. And when we look at the enlarged view, what we really had was we ended up in a typical learning studio, and there's 62 or 63 of these on this project. Typical learning studio had 2x4 light fixtures. We had a perimeter zone, which is tagged as A, controlled by the perimeter daylighting control, and we had the interior zone, which was controlled by an occupancy sensor. We set the classrooms up to be controlled on a vacancy, meaning the lights do not come on when you first walk into the room. You have to hit the controller on the wall, that keynote 4, to turn the lights on. If the occupancy sensor then does not see movement, it will then shut off. The reason for that was, we didn't want somebody to, forget their keys or their cell phone, and when they went into the room, all the lights come on when they were only there for seconds. But the lights would then remain on for 15 minutes. So we wanted to make sure we had that conscious effort to turn the lights on when there is class, and then we let the automatic controls take over from there in terms of the daylighting zone as well as the interior for the lighting. This is a typical floor of the project, and again, you'll see where we had all standalone controls for the project. And the classrooms, again, were controlled on the vacancy that I just described. However, the corridors, for both safety and security, the corridors are controlled on occupancy. So if someone comes in and walks down the hall, those lights will turn on based on detecting them as an occupant within those corridors. We did that for a couple of reasons. The real reason we weren't comfortable, I think, having spaces that were dark if the building is occupied. And the other reason is really for security as well. If someone were to be running around this building, which I understand happens sometimes in high schools and middle schools and elementary schools, we'll know exactly where they are because the lights will turn on in front of them. So That was the majority of the building. We do have some spaces that are on standalone time clocks, and we do have some spaces that have integral motion sensors that dim to 50%. An example would be the stair towers or the egress paths. We never let those go dark, but they do, upon entry into the stair tower, the lights in those will increase from 50% to 100% for egress, as well as communication. I think we're encouraging, obviously, students to take the stairs and not use the elevator in a net zero energy building. This is a picture taken on a cloudy day quite a bit ago, March, I think, or so. And you'll see sort of in that middle level, which is in this case, the third floor in the middle of the screen, you'll see with that classroom on the left has those 12 fixtures or 9 fixtures that are on. And then that classroom on the right really has most of the fixtures that are off. So the sensors are working. It was a cloudy day, so the daylight sensors didn't have some of those lights off, obviously, because we weren't meeting the foot candle levels. We had a strategy for plug loads. I mentioned earlier that we were looking at those 4 or 5 categories: envelope, HVAC, service hot water, lighting, and plug loads. Within the individual classrooms, we did a very similar document. We're looking at the receptacle loads. And the receptacle loads in the classroom, because we had interactive smart boards as well as computer loads, that smart board receptacle is connected to the occupancy sensor. So in the room. So that works very similar to the lighting, where the teacher would come in and turn those computers on and turn the smart board on to use it. And then once the room is vacated, the occupancy sensor, that same controller that's controlling the lights, will actually turn off the smart boards. We thought that was important because there's so many electronics happening within those 60+ learning studios. That was important not to just turn them off when they were not in use, but to turn off the phantom loads as well. So they're not running 24/7, 365, even in the phantom loads. So we were able to reduce our receptacle loads within the classroom by having those shut down. So sustainable strategies for reclamation. So we studied 3 different systems working with our contractors, design build partners. We looked at water source heat pumps. We looked at a variable refrigerant flow system, and we looked at a 4-pipe fan coil system. We ranked those with everything from space to architectural impact, ease of operation, technical maturity, first cost, energy cost, etc. And when we evaluated those systems, we ultimately determined that the VRF system was a better system option for this project. The systems we used for the VRF, they are actually a water-cooled variable refrigerant flow system. The water-cooled comes from the geothermal system. They are water-cooled and both cooled, and we have heat rejection as well that goes in. The variable refrigerant flow has energy recovery within the individual refrigerant components. And that system is used to heat and cool the building. It is worth noting that the VRF system we have is independent of the ventilation air system. So those systems are decoupled. We've been doing that for quite some time. It's better for energy performance. For one, decoupling those systems so that we don't need to, for example, distribute 100 units of air to heat and cool a space, even if no one is in that space or it is very minimally occupied. The other benefit that decoupling has of those systems is it actually has a very healthy component to it. So when we decouple the ventilation air and the heating and cooling terminal units, we don't have any air that circulates from one classroom to another. The ventilation air is a once-through system, and then it goes to the heat recovery and is exhausted. And each classroom has its own terminal unit or independent individual terminal unit. So no air is actually shared between the learning studios themselves or to the corridor for that matter. So that became an interesting discussion, and that's a design that we've been using for quite some time. What that design really lets us do is when we started talking about pandemics and COVID and all of those things, we didn't have classrooms communicating with another class or another classroom. And that became a very good component of a design, versus say, some existing building infrastructure out there that has a packaged rooftop unit that serves all classrooms and the air is recirculated. That has a different approach, a completely different approach to it when you talk about health in a building and filtration and isolating individual rooms. So this system allows us to do that and treat any individual room and not recirculate or circulate and redistribute contaminants from one classroom throughout the building, which was pretty nice. This gives you that same section again. We did connect to a geothermal system, is largely under the new softball field. What's cool about this design is we used the geothermal system and then we stacked our mechanical rooms in the building. So this got a couple of things for us. Within the building itself, we're able to shut it down systematically during the day or at the end of the school day, I should say. And the idea is that, when you have the layout of the existing high school, when they would have an after school activity, they would have to keep virtually the whole school on because of the mechanical system it had and because of the layout it had. With this building, we're able to systematically shut down either one half of a floor or an entire floor and systematically shut it down at the end of the day. So within the design itself, a lot of the public space or a lot of the public use space or a lot of the after school space is all down low. And we have laboratories for the most part in that 5th floor wing up high on plan west here on the top floor. So we're able to shut those systems down on those floors. And the idea is that we systematically shut the building down from top to bottom as we progress from the end of the school day into evening activities and then ultimately to the building being in setback mode. So we're able to shut off those floors and put them in unoccupied mode and really start to systematically shut those things down. So certainly after school items, whether it's DECA or French Club or what have you, those things we'd like to see scheduled for the lower floors, and we shut down the upper floors as the day moves into night. So that isolation became important, and then the geothermal field you see here on the right. This shows 2 of the drilling rigs. At one point, there were actually 3 rigs on site. We have 190 wells that were drilled over here in the fields. In this view, you actually see Gilbane's trailer on the right, and that's actually the middle school in the background. So this view is kind of looking southeast, I guess. So the wells were pretty amazing. For those people that were out there and saw them, I have a video separate from this where we were able to video them extending the piping about 500 feet down and back through the wells. And it took minutes, to extend that tubing down and back. It was quite a chore to do the 190 wells, but it worked out really, really well. So this is going back to, we combined the variably refrigerant flow system with dedicated outdoor air systems with energy recovery. And again, those units, the energy recovery units, the ventilation air units, are in those floor-by-floor mechanical rooms as well. So again, having them floor by floor allows us to shut down floor by floor. It also allows for operations and maintenance staff to gain access to these rooms, even in inclement weather. All mechanical components are indoors. A couple of reasons for that. It's the maintenance piece really became a byproduct, but the goal was really to liberate the roofs of both wings and make them available as much as possible for the implementation of the photovoltaic panels on the roof for energy production. We do have a handful of fans or a handful of DX systems on those roofs, but for the most part, they are liberated and wide open for the installation of the PV panels. This is a picture of one of the mechanical rooms. This is the VRF component, and really what you have is within an individual wing of the building, there is an A side and a B side of that wing. So in this case, it's A1 and B1. So it's really within an individual wing, we have 2 halves as well. So I mentioned before that we could shut off either a wing or a floor. With the way the VRF is split up, we can even shut off a half a floor, a half of a wing of a half of a floor. So really the building from a heating and cooling standpoint, each floor is broken up into quadrants. So we could shut down with knowing the schedules and programming of after school events, we can isolate really a quarter of any individual floor. So again, a lot of this came from the existing operations of the high school, of old high school, requiring the whole building to be on when we had after school events or when we had nights and weekend events. So one of the major things we did as well is we have CO2 sensors, demand control ventilation in all of our spaces throughout the building. The student population of the building is today is plus or minus 900 students. It's expandable to 1,200 per the RFP, and per discussions and per design, it's actually expandable to about 1,500 if you were to put it at full occupancy mode. So the building itself has a ventilation calculation that if you added up all the individual spaces, cafeteria, gymnasiums, auxiliary gym, auditorium, classrooms, locker rooms, etc., it has a ventilation requirement that would actually support, if you reversed out the math, it supports more than 8,000 people in the building. So, and each individual space needed to be ventilated and have the ventilation capacity for the individual component. However, the students cannot be in more than one place at a time. So we follow the students with CO2 sensors, and that is how we are able to cut down our ventilation air substantially in terms of the daily operation and how much ventilation air is brought into the building. So all spaces do not need to be fully ventilated at all times. However, any individual space is capable of the maximum occupancy of that space. What's on the diagram here is when we isolated just the cooling for the building, about 48% of the load within the building goes to ventilation air. So that's why controlling that ventilation air becomes so important to us, where if we can cut our ventilation just in half, we can cut our cooling load down by 25%. And the reality is, with the CO2 sensors and demand control of ventilation, we cut our ventilation air substantially down throughout the building, especially when the building isn't fully occupied to its planned capacity, or even during modes where we have partial students in the building. So controlling the amount of ventilation air is a substantial way of saving energy within a facility like this. For the service hot water, we were able to do a central domestic hot water system. We did it through a water-to-water heat pump. It's made by Arctic. That's the hot water system you see in the right. It's 2 units that take geothermal water and take the heat out of the geothermal water and generate domestic hot water from there. In addition to that, we were able to do all low flow fixtures, including showers, anything that consumed hot water, showers, sinks, faucets, etc. So the first step was to reduce how much hot water we needed and how much we were consuming. And then the second step was to generate that hot water in the most efficient way possible, which was connecting that system to the geothermal system and taking heat out of that loop. One of the concerns, certainly in the Mid-Atlantic, is that we reject more heat into the ground than we take out of the ground. So one of the ways to combat that argument is to, where we do need heat, domestic hot water, is we take that heat out of that geothermal loop. So this is always taking heat out of that loop, even summer and winter. So we had a host of other conservation measures here. This is kind of a summary. I don't think it's an all-inclusive list. We went through a handful of these, the geothermal, DOAS, etc., daylight responsive controls, plug loads. There's a handful of others in there, including the energy monitor at the front door that's really looking at the energy consumption, and the dashboard as well. So this was our map, our roadmap to net zero. You'll see that we had a median property per Energy Star with an Energy Star score of 50 would have had an EUI plus or minus 60. A baseline, hash rate 90.1, again, prescriptive compliant building would have had an EUI just about 46. And you'll see that all the way to the right-hand side, when we incorporate all the strategies we went through, we got ourselves to an EUI in and around 21. And then the energy production by the photovoltaics produces that EUI of 21. Again, the 21 is a little bit high compared to some other schools. I'm sure there's other schools out there where somebody might tell you, oh no, we're at 12 or 15 or 18. And that's probably true. But with this project, we have compensated that up based on the operating schedule. As I mentioned, there's so many people that use a high school beyond high school students, and this building in particular, that we were able to extend that. And that has created a condition where our EUI is a little bit higher just because the operating hours are so much longer in a high school, say, compared to an elementary school or a middle school. So this is just that same information. We started with that diagram on the right, and you see the proposed diagram on the, sorry, we started with the diagram on the left, the proposed diagram on the right, where we have targeted an energy reduction of the end use of about 50%, 53% in this case. And you'll see where I mentioned earlier, we had cooling, heating, and lighting as the majority of our consumers, and we've cut that way back through the use of energy recovery systems, geothermal systems, CO2 sensors, reducing that ventilation air, the total ventilation air to the building. And then last but not least, we get into the generation strategies. So the generation strategies for this project is a bit of an older diagram, so my apologies for that, but it's close, where we looked at how much area we would need to produce 25%, and then the whole, all of the power for the site. So obviously the roofs of the high school, because we liberated those from mechanical systems, are being used. The roofs of the addition are being used, and there's currently planned, kind of in this diagram, a little bit just south of where it says high school geothermal bore field, in the middle of that diagram, is a parking lot that is planned to have a photovoltaic parking array canopy over it as well. So it's pretty awesome. The power purchase agreement has been done by the owner through to generate that power and to install it. So this is looking at the annual numbers. This is looking at the energy uses in red and the PV production capability of a 1450 kW array overlaid over each other. And you'll certainly see that there are times of the year where we consume more energy than we can produce. And that is in the winter months when the sun is at its low angle and low strength and our heating load is still high. But you'll see in those shoulder seasons and summer months where our occupancy is down, our demand is down, and our PV production is up. And when you total all of those up and compare them to each other, it produces more energy than we would consume. And that is the end of my presentation. I'm happy to take questions. You can plug them into the chat if you'd like. I'll check the chat real quick and see if there's anything in there. You're welcome to plug questions into the chat. I think some of the questions we normally get, have to do with the cost of the project. This isn't proprietary information on this job. The cost of the project was $108 million. The design and construction is more than 300,000 square feet when you look at the construction of the new high school plus the renovation of the middle school where the connectors happen and the shared cafeteria. At 300,000 square feet, that comes out to about $360 a square foot for a net zero high school, not including the photovoltaics. Again, those are coming as through a power purchase agreement, but you can see that it's very much achievable from a dollars per square foot or a cost standpoint. And a lot of what I presented was not necessarily buying the most expensive solution for everything, but buying the most pragmatic solution given the cost constraints and the energy performance, and really looking at what is the right solution for this project. Certainly there's net zero buildings out there that are $600 or $700 a square foot, And I think some of those, you know, probably the cost of those could have come down with the selection, I think, of the right materials and the optimized materials, building envelope, glass, etc. And with that, let me see here, questions.
Hey, Kevin, I see a couple of questions under the questions tab.
Okay.
The first one is, how long did it take to drill a 500-foot deep geothermal hole?
Oh, the individual wells? I'm not sure about an individual well itself in terms of the drilling, but I believe the construction schedule for all of the wells was only 3 to 4 months. And in our case, because it was really it was under an area, it was obviously an exterior area. It had no impact on the building construction itself, and ultimately it landed under what is the fields. So it was done concurrent with the building construction. So there's no delay in sort of the geothermal well field compared to the building construction.
Okay. The next question was heating really only 5% of the overall energy consumption? This seems very amazing. Was this due to superior envelope?
Yeah, so the heating component, yeah, so it's 5%. Yes, I think it's what we're showing is the reduction in that chart, but it's for a couple of reasons. It's one, it has to do with the geothermal and the heat exchange there. It has to do with the energy recovery on the ventilation air, where when we exhaust the air, we are taking as much energy out of that exhaust stream to preheat the air coming in. And then through the variable refrigerant flow system, our heating and cooling system, that system itself has energy recovery in it as well through the refrigeration system. So it's a combination of all of those where we got down to the heating. That number, that 5%, I'd have to go back and look. That 5% actually might be the 5% might have been the service hot water.
All right, the next question, it says, looks like the HVAC system has the best acoustical performance. How much did this factor in?
Well, the acoustics, I mean, it was one of the criteria. So we had an acoustical consultant on the project that evaluated all of the systems, the selected system, and made the recommendation in terms of the noise. I think we met the requirements of LEED for noise. So it was a factor, but I wouldn't say it was a major factor. You know, the major factor for us with those systems was certainly first cost, because we had a ceiling of a budget that was fixed, and the operating costs for the net zero component. I would say those were 1 and 2.
Okay. The next question is what educational features are available to the staff and to the students regarding the building performance? Dashboard ?
Yeah. So there's an energy dashboard that has been provided just inside the front door inside the lobby on the left-hand side that has different screens available, and the different screens ultimately it will look at the PV production when that's available, but it looks at service hot water consumption as well as the energy performance of the building. Yep, so there's a dashboard just inside the lobby on the left.
Next question, were there any cost analysis done on how much this building costs per square foot versus a basic code compliant building?
No, not that I'm aware of. In terms of comparing this to a minimally code compliant building, I don't believe that. If it was done, we certainly didn't. You know, Interface didn't do it. But just from working on other projects, other high schools, middle schools in the area, you know, to get a project like this done for less than $360 per square foot is really, really, really good.
Okay, the next question, why was the solar system left out of the base project?
Money, cost. So it had it was left out of the base 108 million, just based on cost. I think if the project had a handful of million more, it certainly would have been in the base number. And ultimately, it's incorporated into the project through a power purchase agreement. So the PVs will be installed through a power purchase agreement, and it was just the first cost of the PV. It had to be balanced, right? So within the RFP is a host of criteria, and I think the team was able to deliver to the city nearly everything except the PV within that dollar amount.
Okay, and does the school have an air quality monitoring other than CO2?
Yeah, yes and no. We have air quality monitoring stations on the ventilation air units that we can track the information on of the outdoor air that comes in. In terms of inside the building, our major component that we monitor on a daily basis is CO2.
Okay. Next question, is the PV system PPA for the whole school district or just for this campus?
That I don't know. Certainly the design that I know is for this school. I don't know if it applies to the rest of the city of Falls Church or not. I'm not sure. Probably a little beyond my purview.
Okay. PV was not included in the design building scope of work due to more favorable pricing available directly to the district. So I think that's if it's a statement or a question.
I'm trying to see that question. For some reason, I can't see what you see, but I'm trying to expand it. I don't know if that's a question.
All right, well, I think that's all the questions that were put into the system. Certainly, if anybody has other questions, you're free to pass them along, and we'll do our best to have Kevin respond to them and get them back to all attendees.
Okay, thanks everybody.
All right, please feel free to join us in 2 weeks. So we'll have an in-depth discussion about the engineering that goes into building facade design. So that will be on June 16th. And Mr. Steve Gross, Associate Principal with Interface Engineering, will be leading that discussion. Thank you all. Have a great afternoon.